Good morning, ladies and gentlemen. Is it going?
Well, it's got this red.
I think it's fine. Yeah, I don't know why it's doing that.
Let's try it again. On your mark, get set, go.
All right, good morning, ladies and gentlemen. It is a hot 59 degrees?
59 degrees Fahrenheit.
Holy cow. Okay, hopefully it warms up by the time you guys get here. Okay, so we are starting a new unit today. Let's take a look at circle parts.
You gotta know your triangle parts, you gotta know your circle parts.
So we have the diameter, which is the whole way across, our radius, which is halfway, the center.
That's important.
It is important. The circumference, and then the tangent, which is really any spot on the circle, just one specific spot, and then you just draw a line that's perpendicular to that spot. Okay. Let's twirl a string. So when you, first of all, when you twirl a stopper on a string, what happens when you let go? First, let's just go ahead and twirl in a circle here. Okay, what do we have going on?
Got a stopper going around a circle.
Stopper going around a circle. You know, I'm gonna go over this way. I'm gonna hit those lights up there. Okay, and what is going to happen when I let go of the string? Okay, so I am going to spin my stopper in a clock. I've got 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock.
Yes.
I'm doing that backwards, so I hope that's all right. And I'm just gonna go ahead and start spinning here.
Other direction.
This way. Okay.
Oh, wait a minute. No, you had it right. You had it right. I'm sorry. It's backwards in this.
Oh, it is gonna go this way. Okay, so I'm gonna let go at 12 o'clock here. Right there. Oh. Okay.
It went that way. So when she let go of it at 12 o'clock, it went off to the left here as we look at it.
Okay.
But where should you let go of it in order for it to go straight up?
I'm gonna let go of it at 3 o'clock. There we go. And woo! There we go.
And it goes straight up.
And it goes straight up.
All right.
So why is that? What part of the circle determines the direction that the stopper will go?
Well, the string is the radius, and the path it follows.
So if the string is the radius and the path it follows is the tangent, then what determines the path?
It goes along the tangent,
Goes
perpendicular
along the
to the radius.
Exactly. And why does it do this?
I'm thinking Newton's first law of motion.
Has to do with inertia. An object in motion stays in motion.
At constant velocity in a straight line path will remain in motion unless acted on by an outside force, such as the string.
Okay. So the distance traveled for an object moving once around a circle is 2 pi r. You guys know this?
2 pi r. That's the circumference, right?
It is, yes. That is our circumference all the way around. And you need the radius to get that, don't you?
So here's the first part of our motion idea: is the distance traveled for once around a circle is 2 pi r. The next item is?
The time required for one lap is called the period.
Period. What period is this? First, second, third, fourth?
I think we're in 0 period right now. It's too early. Okay. So a period. What is a period? Periodic table. We have periods in the day, don't we?
Yeah, it's a repeating time interval.
A repeating time interval. So our periods are, I think, 48 minutes every day. And we have a repeating time interval for every lap that our stopper and string goes around.
Yes.
Right?
And it's so important it has its own symbol. It's the capital letter T.
It's not lowercase, it's capital. Capital, because it's important. Okay. The speed of an object in circle. Well, first of all, speed equals distance over time, yes?
Yes, ma'am.
And so in circular motion, we are going to go ahead and replace the distance that it travels in circular motion with 2 pi r, because that's the circumference.
That's the circumference.
And our time is no longer regular time, it is our time, our period,
right.
Capital T.
And so the speed of an object in circular motion is just 2 pi r times the period.
Exactly. Okay. The linear speed of an object in uniform circular motion, speed equals 2 pi r over t.
Yep.
Yep. Let's find the speed of this stopper on a string.
I'm gonna go back and get a stopwatch.
Okay.
I hope I can find one that works. Look, there's a bunch of stoppers. Does this work?
So.
Yep.
So I'll
Okay.
write up our data up here, but I'll do it over here so I don't hit things like that. Okay, well, what do we need to find?
Well, 2 pi r, we need the radius of the string.
Okay, we need the radius of the string. Can we measure that? Sure can. My hands are so cold. Okay, so to right here?
No, the center of the mass.
To the center of the mass, right here. So put that there. We will call that 0.46 meters.
0.46 meters.
0.46 meters.
So r is 0.46 meters.
Okay. R equals 0.46 meters. And then what else do you have to find?
We need to find the period, the time for one lap.
And then that's all. So, I don't think it's going to be very accurate if we just do like one circle.
No, Mr. Boykin's kind of not the best for the stopwatch.
We know how Mr. Boykin is with the timer. So let's do 10 circles, right? And then we'll divide by 10.
Yeah.
That sound good?
Uh-huh.
Okay, tell me when you want to go.
Well,
I'll
just
do
get it
my
spinning
thing.
and we'll and say tell me when to start, then count to 10 and tell me when
And
to
we'll
stop.
make the top. Ready? And go. Go.
Oh, wait. I thought you said go. Let's try that again. Now keep spinning it.
Okay.
On your mark, just
Okay.
tell me when to go.
On your mark, get set, go. 2, 3, 4, 5, 6, 7, 8, 9, 10. Whew. Okay.
I get 5.11 seconds for 10 laps.
That's kind of hard to do. You said 5.11?
Yeah, 5.11 seconds for 10 laps.
Okay.
So just right to 5.11 seconds divided by 10 laps will give us the time for one lap. I don't think you're going to need a calculator for that one.
Oh, you're right. So we're going to do
0.511 seconds.
for a lap.
So now we've got the radius, we've got the period. Now we can calculate the linear speed.
Divided by 0.511 seconds. And I get, okay, 2 times, where's that pi? Oh, right there, pi times 0.46. I'm gonna divide it by 0.511, and I get 5.66.
5.6
meters
meters per second.
per second.
That's simple.
It is. It's
They
easy.
should be able to do it too.
Okay, which is exactly what you guys are going to do.
Let's use a
So-
different stopper.
Take down this data. Where is? Oh, it's over there.
It's over here.
That's that long string. Uh oh, is it long enough? Okay, I'll just hold it. I'll hold it from this spot right here. Oh,
Why don't you slide it back to? Oh, here, hang on. Do we have another measurement?
we do. We have 1,000,000 I don't know. Which one do you want to choose from?
The dirtiest one. I'll hold it down here.
So we got 1.15.
1.15. R is equal to 1.15. Write that down, boys and girls. We're not going to do it. All right, let me clear the stopwatch and let's do the same thing we did before.
Ready?
Yep.
Set and go. 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay. I get, boys and girls, write this one down. 7.08 seconds.
Uh-huh.
7.0, that's a time for 10 laps.
Give another look at the board, in case I forgot.
Do the same thing we did here with the other data. Pause this and make it happen.
Okay, hopefully you did that. Well, do you want to go over with them?
Nah.
There you go. That should be easy enough. Okay. Oh, we did that?
We did that.
Okay. As you were twirling the stopper, what was happening to the velocity? Okay, well, you could say, I mean, I seem to be moving it at a pretty constant velocity, yes?
Where you're moving it at a pretty constant speed, there's a difference between speed and velocity.
And that difference is the direction.
That's right.
Right, and so when we look at this going around in a circle, okay, at this instant it's going this way, this way, this way, and you can see it's changing directions, yes?
So the direction is constantly changing. What does that say about the velocity?
Well, it means that our velocity is constantly changing.
Oh, that's very interesting.
So, is this an acceleration? The answer is yes. Yes, it is, because we are changing direction.
Velocity is both speed and direction, and the change of velocity is an acceleration. So any change in either the speed or the direction, don't hurt yourself, is an acceleration.
Is an acceleration, exactly. So we do have an acceleration here. Okay. Instantaneous velocity is the speed and direction at a point in time.
What is an instant?
Like a little sliver, like a little moment, right?
It's a very small slice of time. Could you demonstrate an instantaneous velocity of that stopper as it goes over? That's what you were doing a minute ago.
Yeah, so instant right here. Instant right here. Instant right here.
So in other words, if you took a picture of the stopper as it was going at that, you stop it at that instant, the instantaneous velocity is going to be perpendicular to the string.
And that's important. The instantaneous velocity is perpendicular to the string. Okay.
Yes, it is.
Okay, the direction of the velocity is constantly changing, which means that we have an acceleration. Okay, Newton's first law of motion states that an object in motion will continue in a straight line path unless acted on by an outside force.
So that means that the string is providing the outside force.
Otherwise, it would just go
in a straight line.
In a straight line. Newton asked, why doesn't the moon follow a straight line path through space? How is this like the Earth and the moon?
Well, it's going around a circle. We asked this question before. Do you guys remember the answer? Why doesn't the moon follow a straight line path through space?
It has to do with gravity.
Gravity, that's right.
Gravity is that string that's keeping it there, yes.
It's that thing that keeps you from dunking the basketball.
Okay. Yes. The direction of the net force, causing the acceleration is toward the center. The centripetal force.
It's called the centripetal force.
Centripetal.
Oh, it has the word center in it.
Yeah.
Look at that.
Makes our life easy, huh? Okay, so the direction of the net force causing acceleration is toward the center, the centripetal force.
Because if you're twirling that stopper, how would you describe the direction of the string and the force that's exerted, and it's toward the center, because the direction is always changing. That's the only thing that's true.
Now, what does that tell us about the acceleration? Well,
the acceleration,
if the force is towards the center, the acceleration and the force are always in the same direction, yes?
They're always in the same direction.
Okay, so what do we have here? We have a lovely picture that Mr. Boykin has copied and pasted from Google.
Goggle. Thank you, Goggle.
And, okay, so we have moon, we have Earth, and the string is just like gravity. Gravity is just like the string. And we see that the, okay.
Don't hurt yourself. Don't hurt yourself.
The velocity, in this case, pointing this way, and for us, is going to be going this way, tangential, perpendicular, right?
So what kind of velocity is this? That's the instantaneous velocity.
Yes, at this instant. And then we see that the acceleration is pointing towards the middle, and that's because the force of gravity is towards the middle.
You know, we can let go of the string and the stopper will go in a straight line, but we can't turn gravity off and make the moon go in a straight line.
That would be bad if we did. Okay. Here is our equation for centripetal force.
I've seen an equation that looks like this before.
It's
What
the
is it?
exact same thing. It's Newton's second law. The only thing is we have that C right there.
What does the C stand for?
Well, the C stands for centripetal.
That's right.
Very
Centripetal force equals mass times centripetal acceleration.
As we just said, the acceleration is always in the same direction as the net force, which in this case is going to be towards the center.
Yes, ma'am.
Okay. So here is another equation that we have, centripetal acceleration. Okay, so our centripetal acceleration is going to be equal to velocity squared over r squared. And if you really wanted to know
Not
where
R
this
squared, just R.
Oh, sorry, r. And if you really want to know where this came from, you could whip out your calculus book and take a stab at it, but we don't need to do that.
No, we're not going to do that. No, we're not.
This is Physics 1, algebra based. We are so happy for that. Okay. All that you need to know about this is that we're going to be using it to find the centripetal acceleration.
Yes, ma'am.
Okay. Let's draw a free body diagram of the stopper on the string at the moment just before you let go to make it go straight up in the air.
That is
This is teacher prompts. Okay. Whew. Alright, so draw a free body diagram of the stopper of the string just before you let go. Okay, so here is my stopper. This is going to be my stopper right here.
Yep.
And where is do you use the blue still?
Well, you could use whatever you like.
Okay, so I'm kind of out of breath now. Okay, so where is my force? If my string is right here, should I draw the string in?
Yeah, draw the string in.
It's right here, right?
And put a little X where the center is.
Oh, good idea. Okay, so my centripetal force is this way.
Yeah. And what says velocity, acceleration, and force vectors.
Okay, so my acceleration is also this way. Is that right, like that?
Sure.
Okay, and then what was the other one's? Velocity, and it was going this way.
Let's say we're going counterclockwise here.
Oh, this way right here, like this. And so my velocity is going to be this way.
That's the instantaneous velocity is perpendicular to the radius. Done.
Is that everything?
That's it.
We're good. Okay. If work is 4 times the cosine theta of delta D, does the centripetal force do work?
Well, we got a force, we've got some displacement. What's the angle between the force and the displacement?
Well, it's moving this way, right? And the force is this way. That looks like it's perpendicular to me. So the cosine of 90 gets me 0.
That's right.
So we're not doing any work.
So by definition, there is no work done by the centripetal force acting on an object in circular motion.
And what does this say about the potential energy of a satellite in circular orbit?
Well,
there's no change, right? Work isn't changing.
well, if it's in a circular orbit, it's not going up or down. The radius is staying the same. And how do you change potential energy?
You gotta move up and down.
Yeah.
Like a change in displacement.
Yeah,
don't
and
have that.
or work being done. So if the work done on it is 0, the potential energy
Is nada. Not there.
stays the same.
Yeah. Oh yeah, stays the same. That's a better way to put it. Okay. All right, homework.
Let's show them that little trick about
Oh, yeah.
acceleration and velocity.
Thank you for reminding me. Okay, we'll come back to this in a second. I know you guys can't wait for your homework. So exciting. Okay. So we said our two equations were V equals 2 pi r over t. That was our first one.
Yep.
And then we have A equals V squared over r.
So what happens when you square V?
Well,
You got to square everything in that.
so let's go ahead and put this V into here. So this is going to be, V is 2 pi r over t. And you said we're going to square it all?
Yeah.
Okay, over r. So that's going to be 4 pi
Squared.
right?
Yep.
R squared over T squared.
You just got to square everything.
Squared all over R.
Is there anything we can cancel here?
Yeah, this one of these R's and that R is going to cancel. So we've got 4 pi squared R over T squared equals R centripetal acceleration.
So there's two ways of doing it. You can have v squared over r if you've already got the velocity, or if you don't have the velocity, all you have is the radius and the period, you can do this.
All right, that's the relationship between those guys.
What were those problems again? What was that
Oh,
assignment?
they are to read page 121 through 124, and then you're going to do page 136, numbers 1 and 3, and then page 137, 1 through 3. Good luck.
All right.